Okay. So good morning to all the participants here. Today we have on the fifth day AICT sponsored short-term training program on design of experiments in engineering. We have with us Dr. G. Venkatesh Garu, assistant professor from Mechanical Engineering of Technology, NIT Warangal. And let me read out his short resume. He has worked in the area of advanced manufacturing process and he has pursued his PhD from IIT Roorkee, MTech also from IIT Roorkee in the production and industrial engineering systems. His research interests include hybrid machining process, ultrasonic assisted abrasive flow machining, surface engineering, magnetic abrasive finishing, and he has worked in at RGUKT, MGIT, BITS Pilani UAE campus, and currently working at NIT Warangal since 2018. And sir has many MHRD projects. So currently ongoing is one on abrasive flow jet machining, sorry, abrasive machining, and he has two PhD scholars ongoing. And sir has published nearly 20 plus international journals and conferences. And sir also has conducted one GNAN conference on multi-scale modeling of sheet metal forming and an STTP on learning management systems modules. And today, sir is going to discuss on a very important topic, which is RSM, response surface methodology, followed by some of those optimization techniques. So, sir has extensively used these techniques for manufacturing processes. And since we have covered since yesterday on right from the day one on ANOVA analysis, Taguchi methods, one factor at a time approach, and factorial experimentations and partial factorial experimentations, and later on some of the gray relation analysis and Topsys method. And we have today whole session is going to be handled by Dr. Venkatesh Garu, and he'll be dealing with both response surface methodology, the process, planning, and execution, and later on how we can use these data which we get in for further optimization techniques. So sir is going to walk through us the entire RSM models, and main emphasis will be given on the selection or the process basically. So like Davidson sir was mentioning on the importance of process. So sir will give us more emphasis on the process and what is the inference that we can draw based on the RSM models. Now, I would like to again thank Venkateshwar Garu for accepting the invitation, and over to you, sir. And you may start the session, sir.
Yeah, thank you, Dr. Varun, for the nice introduction. So, good morning, everyone. Good morning to all the professors and the participants here. I'm Dr. Venkatesh, presently working in Mechanical Engineering Department as assistant professor. Yeah. So, I would like to share my screen.
Yes, sir. I have given access. You may share, sir.
So, my voice is clear, na?
Yes, sir.
Is my PPT is visible?
Yes, sir.
Okay, okay. Yeah. So, in today's session, morning and afternoon, I would like to cover the optimization of abrasive flow machining process, in which I will cover how the RSM is applied and how the fuzzy model and Jaya algorithms are applied in order to optimize abrasive flow machining process. So the major parts of contents are introduction to RSM and optimization, working principle of abrasive flow machining, general process parameters in AFM, limitations of simple AFM, and what is the need of hybrid AFM, and different hybrid AFM processes, and summary of hybrid AFM, research potentials, and conclusions. So I divided my presentation into two parts. So in the morning session, I would like to give brief introduction to RSM and optimization, and what is the application of RSM, and what are the functions of RSM, etc. And I would like to explain my process AFM and its state of art, so that in the afternoon session I will be discussing about the case studies on AFM and as well as MAF. So once if you understand the process, then only you can correlate how the process variables are selected and how the responses will react and how optimization helped me and how RSM helped me and how I applied this RSM and how I applied this optimization technique, namely Jaya algorithm, and how I utilize fuzzy logic, etc. So in a overview of today's morning presentation and our afternoon presentation, I would like to give details about my complete research on uh, DOE, design of experiment. Mainly I concentrate on RSM and J algorithm and fuzzy logic, etc. Right? So how these help and how we are improving our methods and how we are uh, developing a new product and improving the existing performance of the machine, etc., using these techniques. Right? So let us start. Introduction to RSM. So response surface methodology is a collection of statistical and mathematical techniques useful for developing, improving and optimizing process. It is used in the design, development and formulation of new products as well as in the improvement of existing product designs. So in my case, when I was doing my masters, so I have one challenge to develop a new product, and that product is used in my machining purpose. The product name is abrasive media, abrasive flexible media, which is used to finish the integrate geometries, right? So that is a new product development. So I have done literature on existing products, commercially available products, and after finding all the results, I applied RSM, response surface methodology, in order to give the best result. Based on RSM, we have also conducted optimization in order to find out the best among the existing products. I'm just telling an example. Yeah. So what is optimization? Optimization can be defined as an act, process, or methodology of making something as fully perfect, functional, or effective as possible. Specifically, the mathematical procedures involved in this. Optimization characterize the activities involved to find the best. So, whatever your problem may be to develop a product or to prepare or to function any machine with some novel thoughts. So in order to find out the best, you take a simple example. If you want to prepare a tea or coffee in your house, right? So we have input variables, we have dependent variables and independent variables, such as your output should be the taste of the coffee, right? And what are your input variables? The amount of sugar you add, the amount of milk you add, right? And the amount of coffee powder you add, right? You can add uh, means you can add like the quantity of milk and the quantity of sugar and the quantity of coffee powder. The combination of these three input variables will give rise to best output, right? So how much quantity you have to add and what is the temperature you have to maintain and what is the percentage contribution of your milk, coffee powder, and sugar. So the combination of these parameters will give rise to an output called the taste of the coffee, right? Just an example. So why we do this optimization and why we require the best among the existing. So that is important here. Yeah. So optimization, identification of factors, screening of factors, and the response surface methods gives rise to optimization. So identification of a factor. whatever the problem may be. So first you need to identify the factors that define a process. Property is identified. After discussing a brief introduction to RSM and optimization, so we'll discuss my particular process and how I identified the factors in it, right? Next, screening of factors, right? So if already there are factors, you can directly apply the RSM and you can get the objective function, right? So screening of factors. So if there are factors, then you need to screen it, right? Screening to identify most influencing factors, right? So in any experiment, either some people may be working on EDM, some people may be working on ECDM, AFM, or any process. First, you need to identify the factors. What are the important factors and their levels, right? Maybe based on literature, or maybe based on doing some pilot experimentations, you will get some idea, or maybe based on the environmental conditions and the practical problems which you face during experimentation, you will get certain idea. Based on that input, you need to screen them. You need to screen them. So which are important and which are not important. Not important means which are influential parameters, factors, and which are not influencing factors. And next is optimization and identification of a design space. Using response surface methods, you can optimize and identify the design space for these input variables and the output variables. So this is just to brief what is optimization is, and when we are discussing about my process, I will explain you in detail how to identify and screen the parameters, right? So I would like to show some history as well on RSM, right? So mainly, so when this RSM has first taught and first published, right? So in the Mead and Pike paper in 1930s, RSM was first introduced and they developed some response curves. In 1935, another scholar also worked on it. And majorly Hill and Hunter review, they state that a review on response surface methodology, the literature was published by Hill and Hunter, and purpose was to review the practical applications of RSM in chemical and related fields, right? So this is just to know when this response surface methodology has started and how they quoted in various papers and what majorly they worked on. They worked on some chemical and related fields, right? So in 1976, another paper published a review on response surface methodology from a biometric viewpoint, and it was published by Mead and Pike. Right, in the passage of time, many statisticians worked on RSM for implement. Right, so nowadays we see various experimental works, various fields like in medical field, automobile field, manufacturing field, pharma, everywhere they apply this response surface methodology or the design of experiments, and they do all this statistical work in order to give us the better, right? In order to give us the better. So a lot of work has been done nowadays using RSM. Yeah. What actually RSM generally, what are the main objectives? So RSM uses various statistical, graphical, and mathematical techniques to develop, improve, or optimize a process. Also used for modeling and analysis of problems in our response variables in influenced by various several independent variables. What are the main objectives? Why we prefer RSM is to optimize, to develop, and to improve wherever necessary, right? So in some cases, optimization is very critical, right? Why? Because if you want to give the best with less resources, you need to optimize it, right? So in order to do optimization, we should have some techniques. So like that, RSM will play an important role in order to optimize and in order to develop a product or in order to improve the existing one. Yeah. RSM is used in different fields of real life like industries, agriculture, electronics, medical field, and many other fields. Just for an example, if you see in medical field how this RSM will be used, a single tablet is introduced in market after large number of experiments. You can see the application of the design of experiments here, right? Suppose a company want to introduce a new painkiller tablet in market, the pharmacist will make the table that will be more effective and has rapid action to kill the pain, right? Will have low price at market for patient, right? So the function here is to kill the pain. So that is our objective, to the tablet should work in order to kill the pain, right? And what are the variables? Variables are it should be available at lower cost, right? And how the number of experiments can be minimized here, right? By applying a proper method, by applying a suitable method here, right? So a pharmacist can form a table, can make a table in order to develop a new product, in order to develop a new product. Here in pharmacist, say a tablet, a new tablet, and he can give the best out of it by using the minimum resources. So that is the idea here. Yeah. Strategy of experiment. So here various scholars are present in our program. So every scholar will have certain strategy in order to perform experiment. Like I have done my masters, mine is purely experimental, and after that PhD, experimental plus simulation. So we should have certain strategy, and the strategy of experiment is important. And these tools such as DOE, RSM, and optimization will guide you in a proper way in order to achieve your strategy, right? So first, when you start your process, you should have idea about the known factors. So what are the known factors in that process and unknown factors? So if the factors are known, then you can estimate efforts and interactions, right? So what are their effects and what are their interactions, right? If the process, if the factors are unknown, then you need to screen them, right? You need to experiment them, and then you can estimate the effect and interactions, right? So when there is a curvature, right? After if you observe any curvature, then you have to go for the response surface methods in order to optimize by using the tools such as CCD and BB, right? Central composite method and box Behan method, which are part of response surface methods, right? When there is no curvature, means when there is no effect and when there is no the maximum point, minimum point, and when there is no a curvature, then directly you can confirm it, and if no, just go for backup, or if yes, just celebrate. So that is your strategy. Means when you are doing any experiment, if you take a simple experiment, lathe machining of any uh, any material using a lathe machine, right? So you have to know the factors. So what are the influencing factors in the lathe machine? For example, depth of cut, the cutting speed, and the feed. And there may be some unknown factors as well. So that are like what is the temperature raised during the machining, that may be the unknown. You may screen it, you may use the proper instrument in order to measure the temperature raised due to the friction of the cutting tool and the workpiece, right? And if the factors are known, for example, if you have a strong literature on whether if you know the factors and if you know the ranges of the factors like speed, uh, cutting speed, either high or low, or feed, either high or low, or the depth of cut, either high or low, and what is the combination of it. For example, if you take high cutting speed, low feed, and low depth of cut, then you will get certain output. And if you vary them, you'll get a certain output, right? So there is a chance of getting a curvature. So if you are getting a curvature, then you use the help of response surface methods, and then you execute the result. Our job is to have a better removal rate and better surface finish when you are working on a lathe machine, and also in order to have a precision machining and to get an accuracy of reaching the dimensions as per our design, right? When you are working on turning process using a lathe, right? In order to achieve that, you have to make a strategy that how to utilize your resources, how to utilize your known factors, and how to vary them, and how to optimize them, and how to get a curvature, and how to apply these methods in order to get the best output of them, right? So the best output here is the better surface finish, good accuracy of the machine sample, and a better material removal rate, right? There are many other factors, like when you perform the experiment, there are many other factors will come, like the environmental conditions, and maybe the tool may get blunt, maybe there is a breakage in the tool, there may be vibrations in the workpiece. So all these environmental factors also you need to take into consideration while doing the experimentation, right? So finally, if you make a table and if you apply these principles of RSM and other any other optimization technique, that prediction data should be useful to the others who are working on a same material or same tool. So that will save a lot of time and also a lot of money, right? So that will reduce your manufacturing cost, right? So in any process you take, you have a better strategy of experiment. So that strategy is important. Yeah, let us see. RSM resolve around the assumption that the response is a function of a set of independent design variables. They are x1, x2, x3, so on up to xk, say. And the function can be approximated in some region of polynomial model. So you can see the polynomial model in the slide. So here the response variable is y, that depend upon the k. So here the y is dependent, and x1, x2 are the independent, and the combination of these k values will be independent, and y will be the dependent, which is an function or objective function of this study, right? So if the factors are given, then directly estimate the effects and interaction of model as described in the figure, right? So if the factors are known, so maybe you, based on your experiment study, whatever the field you are working, either farming, welding, or machining, so if the factors are known, then directly estimate the effect and interaction of the model, right? So if the factors are unknown, then first calculate them by using a screening method, right? So we can use the screening method here. You can see estimate the interaction effect using first order model. So you can see the first order model, and if curvature is found, then use the RSM model, and the second order model will be used to approximate the response variable. So this is the second order model, and this is the first order model. So if the factors are known and there is no curvature, then you can use this, and if the factors are known and if there is a curvature, then use this second order model, which is related to RSM. Yeah. So what are we are discussing about independent variables and dependent variables, right? What are independent variables? Independent variables are input variables, are those factors which are at control for the experimenter, right? So these factors are varied in an accepted limits to identify the response it makes on the dependent variable, right? So independent variables are the experimenter will have control on it, right? He will vary accordingly in order to have better output, right? He can vary that maybe based on his experimental conditions, and he will have control on variation of this independent. Whereas the dependent variables are those factors which are studied in an experiment, right? Factors are described to define this independent variable, right? So there are several factors to define this independent variable, right? So in any study, there will be some independent variables, there will be some dependent variables, and some constant variables. That constant variables are kept as constant so that By varying them, there is no effect. Like if you converge them, if you do some set of experiments, you will find some constant parameters, some depending variables like responses, and independent variables like the combination of them will gives you the better result. By doing some literature and the pilot study, one can identify the independent variables, dependent variables, and the constant variables used in the function, right? So we'll see once again that consider an dependent variable y, and there is a set of input variables or dependent variables x1, x2 up to xk, right? So now, just for an example, here you can see y might be the viscosity of a polymer, and x1, x2, x3 might be the reaction time, the reactor temperature, and the catalyst speed rate. And the y will be dependent, and these are the independent. Means the combination of these three may be giving rise to will have the independent nature, and the dependent will have effect on these combinations of this x1, x2, x3, right? So here again, once again, you will see this equation. This is an empirical model which is used for response surface model, and how to generate a model, right? We can go for design of experiments, multiple linear regression technique, and surface response plots in order to generate this equation, right? So this is the second order equation. When there is a curvature, in the factors, then we go for this, right? And you can also see here the curve slope, like the experimental values versus predicted values and how close they are. So here the plus sign indicates the increase in y, and the minus sign indicates the decrease in y, and beta naught is the constant, beta 1, 2 up to 12 are the regression coefficients here, and y is the dependent variable, x1, x2 are the independent variables in the given equation, and it can be either first order or second order polynomial equations. So here these trend curves are the, and also the surface plots which are plotted in RSM will have certain meaning, right? So there are types of plots. Either you can choose any kind of experiment like any manufacturing techniques or pharmaceutical or automobile industries or electrical people doing simulation, whatever. So there are some types of surface plots and the response plots you generally observe when you are studying any paper or any research work on RSM, right? So this graphical perspective of the information is plotted in three-dimensional response plot. So this we will call it as an interactive plots. So this is considering factor 1 and factor 2, and this is the response, right? And how the interaction of this factor 1 and factor 2, and how the response will depend upon this interaction. So this can also be plotted in two-dimensional. We can also call it as a counter plots. So you can see in this figure, this is the counter plot, and this is the three-dimensional plot generally used in RSM. So types of second order response surfaces and their counter plots, right? So first plot shows the surface with a maximum point. So here you can see, so this is your response, and these are your two variables x1 and x2, and this kind of surface plot will shows you the maximum point. And the second graph will shows you the minimum point. In some cases, the maximum, the better the output function, and in some cases, the output function may be minimum, the better, right? And in the third case, the surface with the saddle point, right? So these three are possible in second order response surfaces when you are plotting counter plots, contour plots or the three-dimensional plots using RSM. So RSM can be conducted in a sequential manner, right? So when you start working on RSM, exactly you don't know what is the optimum solution, right? You'll just start with the current operation conditions, right? Current operating conditions. When you start working on any machine, any lathe machine or milling machine or abrasive blow machining, etc., exactly you don't know where you whether you are you don't know the exactly the optimum values. In order to get that optimum values, you need to reach them in a sequential manner. So this box shows that RSM design, and here you are starting as a current operating position, and you will have a lot of sequential steps here, the contours of constant response, and this is a reason of operability for the process, and this is a path of improvements where your response is slowly improving, and this is the reason of your optimum, right? So where you reach the optimum and the results will get converged, and you are giving the best with the less resources available. So you need to reach this by using RSM in a sequential manner, right? So RSM is a sequential procedure. Often when we are at a point of on the response surface that is remote from the optimum, and we want to move rapidly from current point to the optimum point with sequence. So if we want the optimum point where the sources are minimum but output is maximum, then that is called our optimum point, and we move rapidly towards it, right? What is the advantage of this RSM is when you want an optimum point where the sources are minimum but output is maximum, right? This point to be noted, right? Then it is called our optimum point, and we move rapidly towards it, right? So how, like after doing experiment conducting experiments, we have a lot of softwares in order to do RSM procedure like Minitab, design of experiment, and you can also perform in Excel sheet, etc. But how to validate them, right? So validation is one of the important part. If you validate them, then only you can share your data or you can publish your data related to RSM or any like optimization, after doing optimization, etc. We will discuss in the case study like how the optimization can be done and how the results will be validated using various theoretical analysis, simulation, and by comparing the data with other optimization techniques, etc. Right? So experimental method. Validation of model can be done by the experimental method, right? First, you need to do perform the experiments, right? Testing of the sample in the design space, matching the observed value and the predicted value will have certain correlation. So how to know that the data model exactly fits the data? So we always check, like after doing RSM, we always check this p value, r square value, and f value, right? So what is the p value? So the p value for each term tests the null hypothesis, and that should be if it is equal to 0, then there is no effect, and when low p value, say less than 0.05, indicates that the independent variable has the significant effect on response surface or on response variable, right? R square value. R square value accounts for the variation of the data. Higher the R square value, the curve fits better, right? So this R square value, P value, F value, generally you will see in various research papers. So after doing certain experiments, after conducting set of experiments and using design of experiment, RSM, etc., you will put a table, and in the table you will also mention the R square value, F value, and P value. And generally, the researchers will look into the values and they predict whether your model can be valid or not, right? R square value accounts the variation of the data. Higher the R square value, the curve fits better, and the maximum is 1. F value. The F value or F ratio is the test statistic used to decide whether the model has a whole as statistically significant or predictive capability. The null hypothesis is rejected in the F ratio if the F ratio is large. If the F ratio is high, then the model is therefore accepted, right? These are the few key points you need to remember when you are working on RSM. You have to go through this p value, r square value, and f value. If there is any problem, then again you have to screen your factors and you have to repeat the experiments in order to get a perfect fit. And if you want to validate your model, So you need to go with this few important factors. You need to do them, like you need to revise them or you need to check them once after conducting the experiments, right? So why to design experiment? Like we can, without that also we can go, right? Why then? Why? In order to obtain the maximum information, like you can see the trend plots, the three-dimensional plots and trend curves, and with less number of experiments, you this effect of parameters is identified, with more information is generated, right? So you can have a lot of data and details when you conduct design of experiment. The aim is to obtain maximum information from minimum number of experiments, to screen factor when large number of factors are present, right? In some cases there will be large number of factors in some experiments, for some studies, etc. How to screen them? Like you can screen them and you can minimize the factors using this design of experiment and RSM technologies, and to get a curve that exactly fits the actual model, right? So we are trying to get a curvature that exactly fits the actual model, right? Experiment has to be designed in such a way that the obtained data exactly simulates the original model, right? So once after doing RSM, the data which generated and the data which you got from the experiment should exactly simulate the original model. Once the model is generated, it can be ready used for the prediction, and as well as it is welcome to the experimenters who are working in the field, so that they can choose the optimum parameters, and they can reduce the time and as well as minimize the total cost by using this predictive data, right? The predictive data by generating the model, right? How to conduct these experiments? Like as I said, like we have various softwares like Design Expert, Minitab, Statistica, expert stat, etc. Probably you might have used this design of experiment, Minitab, etc. When you are generating this RSM table, etc. When you are working, right? The most commonly used are these softwares. I used Design Expert software in my case. Yeah. So screening methods. So screening methods, in order to minimize the factors if there are more factors. So we have some set of screening designs here. So two-level factor, fractional factorial designs, and mixed level. Like you can have Berman design, optimal screening design, etc. Next, response surface design. So once after screening the factors, like you can choose various designs available under response surface, like central composite, box beacon, and also the other designs, so that your number of experiments will be fixed and the number of factors will be minimum, and the number of experiments will be less compared to if you go for the full factorial, right? So these are the factors. So after doing the proper design for your experimentation, probably you can also analyze the points estimated by DOE. So what are the points estimated by DOE? And you can compare them, the experimental points which you actually got from your experimental data, and you can perform some prediction out of it, right? Yeah. So coming to this central composite method, I also use this central composite method. So what is the application of this and what is how it works, etc. Right? A box Wilson central composite method, commonly called as central composite design, is an important experimental design which gives a response curve that suits a second order polynomial quadratic empirical model, right? A second order model can be constructed by using this central composite design, and it's a combination of first order to the power of n designs, factorial designs, plus center and axial points, right? It contains an embedded factorial or fractional factorial design with center points that is enlarged with a group of star points that allow estimation of curvature and formation of second order model. So you can see here the fractional factorial, full factorial, and the star factorial, and we can also see that interaction, iterations, and finally the central composite design, which will give you a lot of information about your experiments, the interaction of variables and responses by using this design with the minimum number of experiments, right? Lot of information on variables and responses with minimum number of experiments, right? The major applications of RSM nowadays, you can see the most frequent applications are in the industrial area. So RSM is important in designing, formulating and developing and analyzing new specific scientific studies and product. It is also efficient in improvements of existing studies and product. Yeah. The most common application of RSM are in industrial, biological and clinical sciences, social sciences, food sciences, and physical and engineering sciences as well. We are concentrating much on the engineering sciences. All this RSM is helpful and useful, etc. Yeah. Coming to background, from now, like in morning session, I will explain the background of my process and the parameters, factors, principle, and the hybrid variants, etc. in this morning session. And in the afternoon session, I will show you my results. I will explain my results, how I applied RSM, and how I validated data, validated my experiments using RSM, and how I compared this RSM with fuzzy approach, and finally how I performed optimization using this RSM, etc. All those case studies, experimental results, simulation results, etc. we'll discuss in the afternoon. But in order to understand them, like you should have background on my process. So that is abrasive flow machining. So we'll discuss the background of this abrasive flow machining in this session. So before closing the morning session, we'll discuss about the process, right? So abrasive flow machining is one of the non-traditional finishing process which is used to finish or upgrade the targeted surfaces which are complex in shape, right? So here the advantage of this process is you can machine the intricate geometries or the complex geometries such as turbine blades, or if you take a nozzle which we use for gas welding, etc. So if your job is to finish the internal geometry of a nozzle, then you can't finish it with the grinding or honing or lapping process, which are conventional processes, because there is a difficulty in reaching the target surface, right? So in order to address this such kind of problems, so here abrasive flow machining process we use a flexible tool, means the tool is flexible in nature, so that if you pressurize that tool to the target surface, so it will reach and it will finish or it will remove the burrs, etc., and it will perform the machining, right? So now let us see the important factors, important parameters, important principles, variants in AFM process. So first is pumping an abrasive laden medium through or over the component to be finished. So what is the principle here is the medium is pushed from one cylinder to another cylinder either vertically or horizontally. So the medium flows from one cylinder through the tooling into the other cylinder and then returns. Yeah. Let us see the principle now. So this is the setup, hydraulic abrasive flow machining. So here you can see there is one hydraulic cylinder which is vertically placed. Say this is an up cylinder, and there is another cylinder down, which both are placed vertically, right? So these hydraulic cylinders are connected to a hydraulic unit, right? And inside there is a medium filled, which I am talking about a flexible medium. Means the tool medium is here a tool, right, which is used to machine or which is used to finish. It is flexible in nature in this case, and this medium is filled in a cylinder, in a medium cylinder, and this medium is pressurized to move to and fro. Means From down cylinder, you are pressurizing the medium to move to up cylinder. And again from up cylinder, you are pressurizing, means you are applying extrusion pressure to move to the down cylinder. That process we call it as one cycle. Means if you pressurize the medium from one cylinder to another cylinder and from the other cylinder to the down cylinder, we call it as one cycle. And while pressurizing, in between there is a tooling, so we call it as a tooling or fixture, right? So the fixture is placed in between these two hydraulic and media cylinders, and the fixture consists of a workpiece here, right? Say here the workpiece is a turbine blade, and that workpiece is inside the fixture, right? And your target is to finish the turbine blade by using this medium which is filled in the media cylinder. And in order to finish that, you are applying extrusion pressure and you are pressurizing the medium to and fro from one cylinder to another cylinder, and we consider it as a one cycle, right? So while doing this, while applying this extrusion pressure by moving this medium from one cylinder to other cylinder, you can see that the media, which consists of an abrasive particles, etc., will abrade the target surface and it will try to finish. When I show you some small working video, then you will understand the principle clearly. So we have different AFM processes like one-way AFM, two-way AFM, vertical AFM, horizontal AFM, etc. Right? The present figure shows a two-way AFM, means two horizontal cylinders placed vertically each other. So the principle is very simple, and I will explain you the enhancements and the variants, etc. in this process. Right? The principle once again I will repeat. So there are two hydraulic cylinders placed opposite each other, right? And also there are two medium cylinders which are opposite each other, right? What is our job is we will fill the abrasive medium in one cylinder, right? And we pressurize this abrasive medium from one cylinder to another cylinder passing through this tooling, right? So this is our workpiece, right? The workpiece is fixed in our tooling. Our job is to pressurize the medium from one cylinder to another cylinder passing through this targeted surface, right? So now what are the important parts here? The important parts are the setup, which consists of an hydraulic unit, cylinders, etc. And the second important part is tooling. So the function of tooling or fixture is it holds the workpiece and as well as it will guide the medium passing through one cylinder to another cylinder. And the third important point is the flexible medium or the flexible tool which is used in this process. So there are three important parts, or three important machines in this particular machine, right? Now, what I concentrate is what are the parameters influencing the machine and what are the parameters influencing this workpiece tooling configuration and what are the parameters that are influencing this media and its behavior. The combination of these three parameters will influence the response, right? Will influence my response. And what is my expected outcome? Expected outcome is the better surface finish with nominal or marginal material removal rate. Why? Because it's a finishing process. I expect the finishing in micro level, nano level, etc. Right? And also, I'm not targeting a simple geometry. I'm targeting a complex geometry like turbine blade, helical bevel gear, or micro holes, micro slits, etc. So this is my machine. So by understanding the machine, you should understand what are the main parts of the machine and the main factors that influencing the machine. Yeah. AFM media, I talk about medium, right? So medium is a combination of viscoelastic polymer with special rheological properties plus fine abrasive particles. It means in AFM process, in abrasive flow machining process, we use a rheological flexible gel which have the rheological properties, and this gel is mixed with the abrasive particles, right? So that these abrasive particles are successfully carried with the help of this gel and reach the target surface for finishing, right? So let us see this video. Here you will understand how the medium or the tool is flexible in this process. So here in this video, They are trying to finish the manifolds which are used in the car. So you can see this is the flexible medium coming out from this cylinder tube. Yeah, this is the medium I'm talking about. So it is flexible in nature. Like this is before machining and after machining, you can see. So due to this flexibility and with special rheological properties, and these are the abrasives which are mixed. So we all know the abrasives generally used are silicon carbide and aluminum oxide. By varying the size of the abrasive, you can have control on the process, like in finishing and as well as in the material removal, right? So by varying the size of the abrasives also, we can have a control, right? So generally phenomena is if you use lower mesh size, means small grid size of the abrasives, then the finishing will be better, whereas MRR will be marginal. So if you use large workpieces, your MRR will be better. Yeah. Here you can see the medium will be extruded. So this is called as one-way FM. So here this cylinder is filled with medium, and that will be extruded, and it will be sent extruded towards the target surface. So here our target is to finish this internal geometries of this manifold, right? So if there are any burrs, or if you want to remove the small burrs etc present, or if you want to radius them, right? So if you want to do the radiusing job, or if you want to finish it nano level, then we extrude this abrasive medium towards the target surface. So this is my method. So here during my masters, actually we developed a material new material to finish and to extrude. You can see here the finishing of this manifold using this flexible medium. I hope you understand the advantage of this process. Like you cannot grind it or you cannot harn it, right? So if you harn it, you cannot reach this place, right? So if you want to reach all these complex geometries, then this is one of the important process where the tool is flexible in nature, and you can only thing is you can extrude it using a extrude horn machine in order to reach the target surface. Yeah, you can see the part, finished part with a better surface finish compared to the actual part. Like after casting this, the surface finish will be very high actually. So the surface finish plays an important role in automobile parts. So if the finishing is better, then the performance will be better and the functionality of the parts will be better, right? And also the fatigue life of the part is also very important. When the parts are continuously undergoing to fatigue loading etc, these automobile parts are mainly the medical implants which are introduced, which are generally used by using titanium alloys etc, which are rejected in our bodies, which are like finishing is very very important, right? So nowadays there are some advanced methods to have this medical implants etc by using 3D printing technology etc. But however, the finishing uptime is important. So if you want to have a better finishing, then you have to go for advanced processes like abrasive flow machining. I hope after seeing this video, you could have understand the importance of this process and how this process is different from the other processes, right? Other processes like the tool is fixed, and it will be the tool will be not flexible, right? Whereas in this process the tool is flexible in nature and it can abrade the target surface. And another important point here is how this flexible tool is made, and how this is maintained, and how this control, and what are the parameters out of it. That is an interesting part here. Yeah. Let us see the another important part, that is tooling. So this tooling is critical here. Why? Because it should hold the workpiece and as well as it should guide the flexible tool or the medium in a proper direction. Otherwise, like you cannot finish the target surface, right? So you should have proper guidance. That proper guidance will be given by the design of the tooling. So that's why the tooling is also very important. And in order to have a better constraints, if you maintain the proper constraints and if you restrict the medium to hit the target surface, then you'll have better results. So here in this figure you can see the tooling for simple AFM process. So here the fixture and as well as the cylindrical workpiece, our target is to finish the internal geometry of this cylinder, right? And this fixture will guides to reach the medium in order to finish this geometry, internal geometry of the cylinder, right? So we have to advance this tooling by using various mechanical devices. Here you can see, in order to have better functioning of this tooling, to have better holding of the workpiece and as well as guiding the medium. So the various applications, as I already discussed in this process, like the various applications of this abrasive flow machining are in medical implants, turbine engine parts, automotive parts, dye polishing applications, etc. So what are the process parameters in AFM? So this is one of the interesting point here. So when we are talking about design of experiments, optimization, etc. So first you need to identify the parameters in your process. Either it may be AFM or EDM or ECM or ECDM, etc. Any process, laser machining, or any process, first you need to identify them, identify the process parameters first, right? And you can, then only you will you will understand where the response and the interaction will lies, right? So as we discussed our process, the main part is the machine settings. So extrusion pressure, so how much pressure you are applying to your tool, number of cycles, so how many cycles you require in order to get the better response. In my case, my response is better surface finish, and flow volume and its speed. So what is, like we are working on a semi-solid medium, so we need to also have a control on the flow volume and its speed, right? Coming to abrasive medium formulation, right? As I said, it's a combination of viscoelastic polymer mixed with abrasive particles, right? So, what are the factors that will influence and that are independent in order to have a dependent, better medium, right? So here, machining settings, you should have a control on pressure and the number of cycles, flow volume, and speed. And similarly, in the abrasive medium also, you should have control on the medium viscosity, right? So you are working on a semi-solids, so the viscosity should be properly maintained. So if the viscosity increases or decreases, then there is a chance of variation of the media behavior. And medium rheology. Rheology is a special rheological properties of the medium. It's also a part of study of viscosity that will be controlled and that will be maintained by means of using the rheometer, etc. You can perform the rheology, and also you will study the creep and fatigue behaviors of the developed medium, so that how it will influence the finishing, etc. Next, abrasive type, size, and concentration, right? So we discussed that the tooling is flexible in nature in AFM, whereas the type of abrasive means either you are using a diamond powder, silicon carbide, or aluminum oxide. So diamond powder is very costly, and we may not offer that diamond powder. Maybe for particular application, for precision applications, maybe that can be employed. Generally, commonly used is silicon carbide and aluminum oxide, and the type is important and the size is important. As I discussed, the size of abrasive will influence your process in terms of the responses and the concentration. Here the concentration is the percentage of abrasives mixed with the percentage of the semi-solid rheological viscoelastic polymer, right? So how much concentration you are adding your processing oil, how much concentration you are adding your abrasives, and how much concentration you are adding your viscoelastic polymer. Like as you seen you in the video, the abrasives are mixed with the semi-solid, and it looks like high viscous, right? So the concentration is important, right? So generally we use 60% of abrasives mixed with 40% of polymer gel, right? You can also use 50% of abrasives, 50% of polymer gel, but you have to have a study on experimentally and as well as the literature knowledge that what is the influence of concentration, or what is the influence of abrasive type, what is the influence of abrasive size, what is the influence of viscosity, rheology, pressure, etc. First, you need to have an idea on these parameters and their role on the process, right? That's why we always consider literature is an important study for any scholar, for any researcher. Maybe by doing the good literature only, then only the candidate will understand the process behavior and the variables behavior on the response, right? After that, if there is any conflict when he's doing the experiment, probably he can cross check or he can innovate a new product, right? If there is any conflict, and if there is a new means, if there is a proper strong reason for that conflict, or by introducing a new product, etc., if there is any better improvement, then probably that will be a big breakthrough. And in order to get these breakthroughs, these tools are used. They are RSM and optimization tools, etc., in order to present your results, right? So after doing certain experiments, certain study, in order to present your results, in order to have a validation to your study or the results, this will give, these tools will give, plays an important role. So every scholar, every researcher who worked on various machines will have a control on literature, and then they use these tools in order to present their data and validate their data. Like as I said, we developed a new product in my during my MTech, and we patented it. Our new product, what we changed is, we didn't change the abrasive type or we didn't change the abrasive size. We changed the polymer used. Like generally available polymer is chemical based actually. So that polymer we have changed here in my study, and after changing the polymer, we recorded the results. We recorded the various results, and we observed that there is a better finishing, better improvement compared to the existing one. And also the developed polymer, the used natural polymer which we replaced from the existing, is eco-friendly, whereas the commercially available is not eco-friendly. Means they are using a lot of chemicals in order to get that shape, in order to bounce the ball, or in order to make the playable nature and the flexible behavior, etc., right? We avoided that chemicals. And we developed a new product here. And by for developing this new product, I would like to tell you, we use these techniques, like the set of experiments, the design of experiments, and RSM, etc. We use these techniques to validate our data, and to showcase that this product is better than the commercial product available by validating the results. So for validating the results, you need to have experimental proof, simulation proof, and as well as statistical analysis is also an important role. So that's why we are concentrating more on the statistical analysis nowadays, like in order to validate, right? The third important here is the workpiece configuration. So restricting passage length and area, and workpiece hardness. So what is the hardness of your workpiece you are using, that will play an important role. And the restricting passage, as I said, when you are developing a tooling, how restrict, the how much you restrict the passage, that you can improve, in the surface finish. Yeah. So this is about the process. Now, while discussing on the advantages and the limitations of the existing process, so here you can see few things. AFM can finish inaccessible areas. As I said, the turbine blades are like you can see the engine, the part of engine of automobile also was finished in the video you have observed, right? And the complex internal passages or components are can be finished. It can save 80% of cost of final finishing component comparatively manual, right? And easy to operate. like you can see the principle is very simple. So you are just pumping the medium from one cylinder to another cylinder, passing through the targeted surface, right? And the component can finish with high tolerance. So this is one of the capability of AFM. So you can finish at high tolerance, and finishing rate will be also little slow. That will become a limitation that we'll discuss. Yeah. So being such a good process, there are also some limitations. One of the major limitation is low material removal rate. Means low finishing rate. Means it requires lot of cycles and lot of time in order to finish that. Right. So it increases the processing time and the finishing rate. Right. So, being such a good process, there are some limitations such as low material removal rate and low finishing rate, we can say. So, now what is the need for hybrid AFM process, right? So, once you understand the process and the process behavior, right, then you will also look into the applications of the process and as well limitations, right? I know the applications of the process and also the limitations. Now one has to study how to overcome these limitations, right? So by like various researchers have hybridized the process by adding two or more non-conventional processes in order to minimize means in order to improve the finishing rate, right, in order to minimize the time required for machining. So in order to do that, they have hybridized the process by adding two or more conventional processes. Right? Why we do hybridization? So finishing a surface of advanced materials, finishing up to nano level, improving the efficiency of the process, and to achieve higher material removal rate, we generally do hybridization. Why I'm discussing this means in the case studies, we worked on the hybrid AFM only, right? Simple AFM is used to compare. Simple AFM is used to compare, whereas the hybrid AFM results were much better than the simple AFM in terms of responses. So we applied RSM for both simple AFM and hybrid AFM, and we compared the results, right? So what I would like to tell based on my research is like how the product is developed and how the process is improved by using these tools, how you are validating your data, and by how you are means exploring and improving your results by getting this optimality, etc., and by giving the prediction to the society. Okay, means by doing these all validation models, etc., that will be a ready use for the industries, and also these papers will help the new scholars who are working in that particular area. This prediction models, etc., which are developed by using RSM and other optimization techniques will be ready use. Yeah. Let us see. We are discussing about abrasive flow machining area, and we all know the principle of AFM, and we all know the capabilities. We all know the applications of the process and as well as disadvantages of the process. Disadvantage is mainly low finishing rate. So finishing rate we need to improve. Yeah, in order to do that, various scholars have developed various hybrid processes, such as we can here you can see magnetic based AFM process. So they introduce magnetic field in AFM process. Next, chemical based AFM process. Third is centrifugal based AFM process. And fourth is rotational based AFM process. Fifth is ultrasonic based AFM process. So my PhD is related to this ultrasonic based AFM process. And I will brief you why this ultrasonic AFM process has been chosen among the other hybridizations, and how we hybridized this, and where we got the idea from, and how the other factors like response surface methodology and optimization helped me in order to improve the process and the process response, etc., right? So you need to know the difference between the uh, other processes like magnetic based, chemical based, centrifugal based, rotational based, and ultrasonic. So in the afternoon we'll discuss about the case study on ultrasonic based AFM, and also one case study on MAF, magnetic abrasive finishing. So in these two case studies, our intention is like once you know the process, then only you will have an idea about how the responses are interacting and how the factors are influencing the responses, etc. Yeah, let us see. In 1998, Jones and Hull first introduced the ultrasonic vibration to the medium. We all know the abrasive medium is here, and they introduced this ultrasonic actuator or ultrasonic booster, and they vibrated the medium, right? So by vibrating the medium, here you can see the medium is vibrated and also it is extruded, and this medium will come out from here passing through the target surface, right? So the function here is here the addition to the existing thing is ultrasonic vibrations are given to the medium in this process, and the vibrating tool is introduced, and that energize the mixture, right? So by vibrating the abrasive particles, the media is energized, and this process is achieve better surface finish than the existing process, whereas some the disadvantages are also there, like you cannot have a control on the process stability, and it is used only for the blind holes. It is used only for the blind holes. It is not used for the micro holes and the holes which are open, right? So this is one technique. The next technique is magnetic assisted abrasive flow machining. So this is developed by Sejpal Singh from IIT Roorkee. So the basic principle is same here. So for example, the machine consists of two hydraulic cylinders, and there is one medium cylinder here, right? And there is a tooling, and our job is to pump the medium from one cylinder to another cylinder passing through the target surface, right? Apart from this technique, he introduced the magnetic field around the tooling. So here you can see the electromagnets are placed around the tooling, and due to this electromagnetic field applied around the tooling, what happens means they mix this abrasive medium with iron carbon particles. Along with silicon carbide abrasives, they also added some magnetic particles. Magnetic particles are iron carbon particles. So once after applying the magnetic field, these magnetic particles are attracted towards the magnetic field or the tooling. So the chance of upgrading the surface means the chance of getting more interaction, like the interaction of the abrasive with respect to the workpiece has been increased actually because of the applied magnetic field. Means instead of the abrasive medium just sliding or rolling without touching the workpiece, due to the applied magnetic field, the abrasives and the iron particles are targeting towards the surface asperities. So that is one of the hybridization he has done. By applying the magnetic field, he observed the behavior of the medium, and also he observed the responses. And the new parameter introduced in the field here is magnetic flux density. So what is the magnetic flux density applied? So that is a new parameter here in this field. And you can see few results are recorded while machining the magnetic material and also the non-magnetic material. Here you can see the aluminum is finished, and also they quoted that when they are using magnetic and non-magnetic materials, they observed better improvement of finishing in magnetic material because of the magnetic flux lines present, and due to the more attraction of the abrasive particles and also the iron carbon particles toward the surface. So next, magnetorheological abrasive flow machining. So this is introduced by Jha and Jain in the year 2004. So we all know the principle of AFM, and we also discussed about magnetic field applied, right? So these scholars, they have little improved, and they studied the magnetorheology, right? The magnetorheology in the process. For example, what they did is they introduced the iron carbon particles, carbon iron particles, etc., mixed with abrasives. And we all know in the video we have seen there is a semi-solid medium which is mixed with the abrasive particles and as well as iron carbon particles, right? And they applied the electromagnetic field and they study the rheology. So here one interesting study what they have done is, here you can see the abrasive particle is surrounded by many iron carbon particles, right? And they analyze that the abrasive particle is formed with a chain, right? It kind of chain, right? The carbon iron particles form a chain for this abrasive particle, and the tendency of hitting of the abrasive particle toward the target surface increase, and as well as the axial velocity. Here you can see the axial velocity, the force of the abrasive particle in axial direction has been increased, right? It tends to better finish in lesser time, because if there is no chain formation, the abrasive particle may be loosely held and the force of hitting tendency may be less compared to this process, right? In this process, these iron particles are surrounded and it will use rise better energize. It will energize the particle, and as well as it will give better force. Resultant force will be better compared to the actual simple AFM. So here you can see the CIP chain formation of the abrasive particle, and this is an asperity. So the abrasive particle is hitting at an angle, hitting, and this is the flow direction, right? So when the flow increases, so here you can see the chain formation, and the abrasive particle will energize stage wise. Here you can see abrasive particle along with the CIP chains assisting the shearing of the peaks, right? Finally, our job is to shear the peaks, and also to finish the workpiece with nano level finishing, etc. Right? So this carbon iron particle chain helped the abrasive to perform better compared to simple AFM. In the next study, another scholar has rotated the tooling. So we all know what is tooling, right? So the tooling part, he rotated it. So he rotated it instead of fixing it, right? So what happens if you rotate? He used the spindle and he rotated at different RPMs. So what happened means, if you rotate the abrasive medium, tooling, etc., so there is some flushing action, and also the inactive particles also become active after after rotating the medium inside the tooling. So this is also one of the hybrid variant, and they tried to improve the process. They tried to improve the process by introducing a new parameter called rotation speed in AFM, right? So by varying this rotation speed in RPM, they have recorded various results on finishing parameters, finishing effect, and the various parameter levels, right? As I said, every hybrid variant will have certain hybrid parameters introduced, and you need to completely analyze, completely quantify these hybrid parameters. And in order to do that, again, we need a help of this DOE and RSM and other optimization techniques. So here the new parameter introduced is the rotary speed and how it will vary. Next, next, another scholar, he tried introducing a centrifugal force in abrasive flow machining. So I'll explain you how we achieve the centrifugal force in the tooling. So basically, the process AFM principle is simple here. Apart from the AFM, he has introduced a centrifugal rod in a cylindrical bush, right? So here the cylindrical bush is the workpiece, right? This is the workpiece, and in this cylindrical bush, he has introduced this centrifugal rod, and he has rotated this centrifugal rod, and due to that, the centrifugal force has been generated in the tooling area. So this is the center of this centrifugal rod, and due to the centrifugal force generated around the tooling and around the workpiece zone, the abrasive grains have become active, and there is more participation of abrasives hitting the asperities due to this introduction of centrifugal force, and he achieved better material removal rate than simple traditional AFM process. So Here, the new parameters introduced are the rotation of this centrifugal rod, right? And what is the speed they have used and the shape of the rod, right? The shape of the rod also will influence the parameter. That is how it means uh, if you change the shape, then your restricted passage will have a certain effect, right? And if you rotate at high speed, low speed, then there is a effect. Then there is a effect on the process response. So here you can see they used a nylon fixture, and also they, with the help of a simple gear train, they introduced this centrifugal rod inside the workpiece, and they rotated with the help of a DC motor, and they varied the rotation, and also they changed the shape of the rod, and they recorded results out of it, right? And in order to do this again, I'll tell you each and every hybrid variant paper you will find in the internet, how they use this design of experiment, right? Each and every hybrid variant, whatever I'm discussing, like centrifugal force, magnetic assisted, magneto-rheological, simple AFM, each and every paper on net you will find how they applied RSM and how they applied design of experiment for better improvement or improving the process. So here in this case, you can find some papers in which they change the shape by changing the shape of the rod, how the process response is related, and by varying the speed of this centrifugal rod, how the process response is varied. So these are the two factors again which are new to consider. So you have to screen them, and you have to do some pilot experimentation, and if there is any range, if you find any range of this parameter like rpm 50 to 100 etc., in that range you need to set and design of experiment, and need to find out the optimum speed required or optimum shape for getting better result, etc., right? So all this can be done with the help of this design of experiment, and mainly response surface methodology and optimization techniques, right? So here you can see few uh, scanning electron microscopic images of workpiece which are machined by centrifugal assisted abrasive flow machining at different parameter levels. Here you can see with the 250 microns of abrasive, and with 150 microns of abrasive, 100 microns. So that is the beauty of RSM table. So with different levels, with different factors, and with less number of experiments, you can have the better output and better result. So among them again you can find the optimum values, and you can also validate the data with the help of other optimization techniques, right? So these are few results which are presented, and the another scholar. So this is another hybrid variant. This name is drill bit guided abrasive flow machining. So in this drill bit guided abrasive flow machining, basically in order to like in the previous case, we have seen that the centrifugal rod is introduced and they rotated the rod. Right here, instead of centrifugal rod, they use drill bit. They used a simple conventional drill bit, and they have not rotated this drill bit. They have just introduced the drill bit in the cylindrical bush, and they applied the AFM principle, right? what they observed is what they observed is, like, due to the helical flute structure of the drill bit, here you can see the flow along the flute path has lot of influence of influencing the drill bit, right? And there is a reciprocating axial flow and scooping flow. This is done only because of the shape of the helical flute drill bit, right? So this is an schematic analysis, and based on this, they have done some experiments, and they recorded that the surface finish is better, and as well as material removal is also better compared to the simple AFM process, right? So here the new parameter is introduction of the drill bit. Maybe here drill bit is not a variable, we are not rotating it, but the shape and the restricting passage will be a variable here, right? So means the size of the cylinder you are using in order to restrict the passage. means the workpiece configuration will be one of the input variable you need to consider while doing the experiment, right? So by varying it, how the process response will affect, right? By varying the size of the drill bit, how the process response will affect. By rotating it, someone tried, by rotating it, how it will affect, etc. Right. So next scholar tried rotary abrasive flow machining. So he has rotated here. He has rotated, and what he recorded is this is the workpiece diameter, and this is the workpiece height. And due to the rotation of the machine while doing the simple AFM, the protrusions also will carry. The protrusions also will move along with the rotations and will have more interaction. See, this is the workpiece zone, right? So if you are not rotating, for example, the abrasive particles mixed with medium will slightly move from one direction to another direction, and there are more inactive abrasive particles. Inactive abrasives means which are not interacting the asperities, which are just sliding and moving forward, right? Whereas if you like, since you are rotating the machine, the abrasives are also rotated, the medium is also rotated inside, and there are more protrusions, there are more interaction compared to simple AFM, and they recorded better result. So this is done in again IIT Kanpur by Shankar et al. Here you can see. Yeah. So another scholar, Rajesh et al. So in the area of abrasive flow machining, so he has introduced the drill bit. We already seen the introduction of drill bit will gives you some helical flow and scooping flow, and due to its helical behavior, the process response will vary, etc. Right? But what he has done is he has rotated the drill bit as well. Means he is generating the centrifugal force and also is taking the advantage of the drill bit. Right? So the principle is simple here. The simple AFM principle is there. So it consists of two hydraulic cylinders and the medium is present, and we are pressurizing the medium from one cylinder to another cylinder, whereas the drill bit is introduced in the workpiece zone, and the drill bit is rotated as well. So what are the factors here? The factors, new factors are the rotation speed of the drill bit, and as well as and as well as the shape of the, I mean, the size of the drill bit, etc. Right. So what he achieved and what he recorded is, so by rotating the drill bit at higher speed, it will act as a normal rod. Means there is no effect of this scooping and helical fluid behavior. At lower speeds, it has a better effect. So the rotation of drill bit at lower speeds will have a better effect because the helical fluid structure of drill bit will function. But whereas if you rotate at high speed, then it acts as a normal rod and there is no much effect, only the centrifugal force may act, right? So he recorded by using RSM. He has developed a table by using the design of experiment. You can see the paper, like how the rotational speed of the centrifugal rod and how the helical fluid structure and the centrifugal force influence this parameter, and how we are doing the interaction plots and how we are presenting. So that is what important by using this DOE and RSM, etc. Right. Next, coming to my process. Why I explained all these methodologies are like, in order to discuss, and you will understand better when we are discussing the case study on UAFM process in the afternoon session. Yeah. So this is my process. Like we developed means after doing a lot of research in AFM, like we understand that hybridization is necessary. Hybridization is important in this field because in order to improve the finishing rate, and also in order to minimize the total time and reduce the total cost, etc. Right. So here you can see the basic AFM principle is same. So there is one hydraulic cylinder here and another hydraulic cylinder here, and this green color shows the medium cylinder where we fill the semi-solid medium, flexible medium inside, right? By using this hydraulic cylinder, using this piston, we pressurize the medium. Here you can see from one cylinder to another cylinder, and from here to other cylinder, we consider it as a one cycle, right? In between, I talk about there is a tooling, right? This is a tooling or the workpiece fixture, so which is used to hold the workpiece and as well as to guide the medium, right? That is simple example, right? But apart from this, you can see the fixture is modified in design, like we developed a new fixture so that the workpiece is externally vibrated with the help of piezo actuator. Means while while AFM cycle is on, we are vibrating the workpiece externally by using the piezo actuator. So this piezo actuator is connected to amplifier and DC offset, and further it is connected to computer. So here we can vary the amplitude and also we can vary the frequency of this operation, and by varying this ultrasonic frequency and the amplitude, it has effect on the process response. So the new parameters introduced in this area are ultrasonic frequency and the amplitude, right? So these are the two new parameters introduced, and we need to see the effect of this ultrasonic frequency and amplitude and other parameters, and how it will affect and what is the response behavior. That will be a case study. So you can see one working video. Okay, it's not working. So okay, I would like to show you later. Yeah. Okay, I will show the video later. So that video will explain to you how the UAFM works. Okay, so here when you see the schematic for explaining the principle, so this is my cylindrical bush. This is my cylindrical bush, and I'm flowing the medium horizontally in my case, right? So the medium consists of an abrasive particles, and it carries some axial velocity and axial force when you pressurize the medium from passing through this workpiece, right? We apply some extrusion pressure, and this is our target, right? So we are planning to finish the internal geometry of a cylinder. So surface to be finished is this, right? This is simple AFM, right? But after introducing ultrasonic vibrations by using an actuator, so here you can see the abrasive particle is nowhere moving in a unidirectional manner. Actually, it is moving in a unidirectional manner and it is hitting at an angle theta, and the resultant velocity has been different in case of after introducing the vibrations. And there is a cycle, we use sinusoidal cycle here, the rising off and the receding of the sinusoidal cycle with respect to time will have an certain effect, and the rising of the asperities will advance and the receding of the asperities will come down. And also we observe that in simple, by applying the simple AFM, the protrusions of the asperities and the abrasive particle interaction are everywhere. So you will get a nominal surface finish, no doubt, but by introducing the ultrasonic frequency, the time required is less. The time required is less. That is how we'll discuss. So here you can see figure A, simple AFM. The abrasive particle is inactive here and the abrasive particle is active here. So here the abrasive particle is inactive means it is not hitting the asperity, it's just rolling and sliding, right? It's rolling and sliding. Whereas when you applied ultrasonic frequency, then there is some mechanical change in the workpiece, that is in microns. So say for example we use 10 micrometer in the study, and due to these advancements of these asperities, the tendency of abrasive particle hitting the asperity has been increased. Ultimately, the result is the finished surface after doing some number of cycles. So we will see some small case study how the with vibrations and without vibrations, the result will vary. Yeah. So in another figure with the proof, with the with the validation, etc., you can see. So say for example, this is a workpiece and this is an asperity and this is an abrasive particle. So asperity peak hitting targeting at an angle theta. So with vibration. So with respect to time, you can see the different levels. of a sinusoidal cycle when it is rising off and receding off is taken. And in another case, you can see atomic force microscopy of the finished sample. So where the tiny chip of the asperity has been removed. And in the another figure, this is optical microscope. Here you can see the asperities are cut and the behavior of finish and the behavior of the abrasive particle is cut. So what I want to tell is, so the asperity can be cut and can have control in microns. So here this is not a material removal process. So we'll not remove the material like we remove the material in milling machine or lathe machine, etc. So here we remove the material in microns, in very small size. That too will have control. So here you can see the initial finishing of the material itself will take 1 micron. So the initial before doing AFM. So after finishing, you will go to nano level. We'll go to nano level 0.001 micrometers, etc. Right. So this is a super finishing process, and our material removal rate will be very low. It will be in milligrams. So the part which is cut will be in very microchip. So we cut microchips and we do nano finishing. We do nano finishing using this process. Yeah. So by changing the mode, see for example, here one interesting study. So here in the first case, so the actuator is fixed, means the vibration of the workpiece is perpendicular to the flow direction, means the actuator is fixed radially here, and we studied, we recorded the result, right? Similarly, we observed like when you fix the actuator axially, what happens to your response? So you can see in the figure, yeah. So here, so this is the media flow direction, right? This is the media flow direction. It's in horizontal AFM, and we are fixing the actuator axially, means radially, perpendicular to the media flow direction. Whereas if you change the actuator position and if you vibrate the workpiece in axial direction, then there is a change of the process response, right? So what are the new parameters added here again in my process? Ultrasonic frequency, amplitude, and also the frequency in radial direction, and the actuator setup in radial direction and the actuator setup in axial direction. See, we are getting lot of factors. We are getting lot of addition of the factors, right? So if you don't have a proper design of experiment, then it is very difficult to quantify and analyze your data. So that's why, like after analyzing, after screening lot of factors, after screening lot of factors, and after quantifying, means after finalizing various factors of influence, and after finalizing various factors which are constant, and after finalizing which are factors which will have interaction effect. For understand this, we should have a proper literature on the process. So that is what right now we are discussing on the literature of the process. So before discussing the case study directly, I hope you followed, right? So simple AFM and the variance of AFM, how the parameters are changed, and how the parameters are added in every case, and how the modes of vibrations also will affect the parameter, right? So we have done few simulation studies also before fixing the parameters. In the simulation studies, we found that the amplitude which is applied in the ultrasonic abrasive flow machine is not having any influence. So we fixed amplitude as constant 10 micrometer, and we varied frequency. We also observed from the simulation that the variation of frequency is giving better result. Before doing experimentation, we have applied the simulations. We have done simulations using ANSYS Fluent, and we observed that by varying the frequency, there is a lot of improvement in the in the response. So from doing simulation also, you can screen few factors. Like in my case, like I fix the amplitude. I am not going for varying the amplitude, and also by I am varying the frequency. I'm varying the frequency. That is a new parameter, and also I can find out by doing this study, whether whether is there any effect on the temperature, or what is the effect of pressure distribution, temperature distribution, velocity distribution of the medium, right? This figure shows this is the workpiece zone, say 0.0552 to 0.075. This is the workpiece zone inside the workpiece, right? So when you are flowing the medium, my study is when you are flowing the medium with simple AFM, so what is the effect? And by UAFM, by after vibrating the workpiece externally, then what is the effect? So at different microns, what is the effect, right? At different microns. So from this study only, I observed that there is no much difference by varying the amplitude, right? And you can also see the pressure distribution inside, right? And the velocity contour, you can see pressure contour, and this is the velocity distribution inside. So we are getting certain results. If you observe, the UAFM is showing better result than the simple AFM. It may be slightly better, but in terms of experimental, you will find a lot of difference by saving a lot of machining time. So this black color line shows the velocity distribution of simple AFM, and the red and blue shows the amplitude, the UAFM distribution inside the workpiece velocity. And also we have done some calculate means then experimental validation by taking the SEM images, and also by seeing the forces and forces direction in simulation. So in simple AFM, the projections of the forces, the protrusions of the forces are in straight. I mean, when you vibrate the workpiece, then they are hitting at an angle theta. And in order to correlate the simulation and experimental, we have performed few scanning electron microscopic images, and try to compare this. So I'll just conclude it very soon. Means the temperature distribution, like after applying the applied frequency, after applying the applied frequency, the interesting study is like whether we need to whether we need to continue with these ultrasonic frequencies or not. Why? Because so if you like increase the frequency, and if you apply the frequency, amplitude, etc., then if there is any effect in the temperature, then your process performance also will affect. That may lead to changes in your output. So we have studied experimentally and also simulation perspective, and we concluded that by giving ultrasonic frequency external to the workpiece, there is no effect on temperature of the medium, right? Why I am telling is we are using a semi-solid medium, and if the temperature increases, then the medium will stabilize, right? The abrasive particles will stability of the abrasive particle will decrease, so they will settle down. So that we also studied temperature distribution simulation point of view, and as well as the experimental point of view. In experimental, you can see the TGA analysis has been done on the developed AFM medium, right? So similarly, one interesting study I would like to show before concluding. So that is we have worked on a bevel gear, finishing of bevel gear. So the important part is you need to develop a tooling for bevel gear. So this is a flexible tooling for bevel gear. So the function of tooling is to upgrade the target surface, to guide the medium to upgrade the target surface, and as well as to fix the workpiece, like to hold the workpiece, etc. So here you can see the protrusions of the abrasive particles on the asperities. And one interesting study we have made is with simple AFM with zero frequency, and UAFM with 19 kilohertz frequency, and amplitude 10, which is constant, and frequency here is also constant. So and the remaining parameters are similar for UAFM and AFM. Only the thing is we are giving the frequency in one case, and another case we are not giving the frequency. And the remaining important parameters such as processing time, media flow rate, abrasive size, concentration, and media viscosity are kept constant. One interesting study we found is our job is means our main research is to minimize the processing time, right? So by that we achieved by giving vibrations, by applying vibrations to the workpiece. So here you can see a surface finish improvement on the y-axis, and the processing time on the x-axis, right? This black color line shows the simple AFM result and the red shows UAFM result. So what we observed is by processing, means by processing up to 15 minutes of processing time using simple AFM, we achieved 55% of improvement in the surface finish when we compare to before and after, right? Whereas by using ultrasonic frequency at 5 minutes itself, we achieved 63% improvement of surface finish, and we went up to 75% of improvement in the surface finish. The matter here is how we are reaching in 15 minutes we could able to finish only 50% of improvement in simple AFM, whereas in 5 minutes itself you are achieving 60 plus improvement in case of UAFM. Means by introducing the ultrasonic frequency to the workpiece in AFM process, like the process has become more rapid. So coming to conclusions and summarizing, so I would like to show you the machine parameters, media parameters and workpiece parameters in AFM field. Like we'll also have a number game and we'll have proper optimization and RSM etc. in the afternoon session. So the new hybrid parameters introduced are magnetic flux density and current in MAF and MRAF, shape of the rod, rotation of the centrifugal rod in CAFM, drill bit guided AFM, drill bit diameter, rotation AFM, rotation speed, ECAFM, current intensity and voltage, and UAFM, application of vibration, radial or axial, amplitude of vibration, vibration frequency, and the type of the actuator used, etc. These are the newly introduced parameters, etc., in the AFM field. And this is the broad classification. Here you can see. So AFM in shop floor, theoretical models, hybrid AFM applications, and the process parameters. The input parameters are related to machine, workpiece, and the medium, and these are all the hybrid parameters, and the responses are surface finish and material removal rate, right? In this broad classification will gives you idea about the hybrid parameters, variance in the domain, and the theoretical models, and the input variables in the domain, and also the responses which are recorded so far in the literature, right? This broad classification is giving the detail about that, right? So the final summary also you can see about various principles like abrasives used and the workpiece used and the concentration or the levels of the parameters they have selected and what they achieved, what type of medium they have used, etc. And the capabilities here you can see this UAFM process using Inconel 718 we could achieve 0.09 micrometer. When compared to other processes, this capability is better in terms of maximum material removal and surface finish. That's why this process is choose for my PhD degree in order to continue and in order to have, in order to improve the process by varying the direction of the vibration and also by introducing the new parameters, by adding two or more by hybrid variants, two or more energies, two or more processes in order to make it hybrid. Yeah. So a lot of people have done, have worked on various application oriented works like AFM. In the video we have seen they're finishing the automobile part, right? So here a lot of people they have worked on finishing of Viridium micro slits, finishing of diesel flow injector nozzles, and finishing of finishing of channels, finishing of helical gears, bevel gears, and finishing of micro grooves, etc., finishing of burrs. So a lot of scholars have recorded the experimental work in this finishing area, and most of the papers here you can see they use this design of experiments and optimization in order to improve the process, etc. So research potentials. So research potentials of this process are like in UAFM process, many of them not tried to explore the means the residual stresses generated after UFM process, like after vibrating, how the residual stresses will act on the finished components, and also the monitoring of study of the behavior. Like we have studied the behavior in the simulation, but no one has tried the study of behavior of the medium in real time. that can be explored by using some acoustic emission sensors, etc., by introducing them, and we can have a control on the media behavior in UFM process. And there's a lot of scope for optimization of process parameters, like many of them have considered only few parameters such as media temperature, flow rate, flow volume, etc. But there are a lot of parameters to explore, and there are a lot of influencing parameters in the field. Like we have explored that ultrasonic frequency is one of the influencing parameter, whereas amplitude is not showing much parameter. Like that, one can do optimization of these parameters and can set the combinations, like by using this certain ultrasonic frequency and certain extrusion pressure and certain other parameters, how the response will be, and how the when the optimization will come out from this study, and what are the means what are the interactive plots, and what are the most influencing parameters out of it. Still there is a lot of scope, right? So in the afternoon session, I will discuss about the case studies on UAFM process and MAF process. And in that case studies, you will find how we applied RSM and how we used fuzzy logic and how we used Jaya algorithm and how we concluded the influence of parameters, and how we shown the interaction effect plots, etc., in the afternoon session. That case studies will be discussed in detail about this process. So in order to understand them, I explain these processes. Right? If you know the process and process variants, then only you can correlate when we are discussing the case study. Yeah, over to Dr. Varun.
Yes, sir. Thank you, sir. Shall we take up some queries if they have, sir?
Yeah, yeah.
So, anyone, if you want to interact with to Venkatesh, sir, you can unmute and you can ask questions, please.
Sir,
Sir, yeah, tell me.
sir, first of all, I need to thank you, sir, because very nice presentation. Unfortunately, I was not able to attend first 20 minutes due to some reason. Sir, if possible, can you share this PPT after this session, sir? Because before starting this afternoon session, we can,
Yeah, yeah. What
I can personally verify this was that what the session was for the first 20 minutes. If you don't mind, you can share, sir,
Yeah,
with
yeah. What I'm
permission.
planning is I will share the PDF of the PPT and also few papers recently we published in RSM by using RSM and optimization techniques in
Okay,
this
okay, sir.
finishing area. That
Uh,
paper links also I will send to Dr. Varun.
Sure,
Sir,
sir.
one more doubt, sir. Sir, when we should go for this RSM, sir? Simply.
Yeah, RSM you have to go when you are getting a curvature actually. When you are getting lot of factors in your experiments,
Oh,
and if you are not getting a curvature, then you will go for RSM plots in order to minimize and in order to screen the number of factors, and you will explore it using this RSM. Yeah.
okay, sir. Sir, is there any limit that minimum or maximum limit of factors? Suppose if we are going ahead with the 3 or 4 factors and 5 levels or 3 levels, on the time we should go for this RSM. Likewise, any restriction or minimum or maximum factors and levels are there, sir, for the RSM?
Means you have lot of options. So like full factorial, central composite, box Bacon method, etc. And you'll
Yes, sir.
also have Taguchi method, etc. Always you should remember that like how many factors you have
Uh,
and how many levels you have. Based on that, you try to go for less number of experiments. So you explore it in a software and try to get a less number of experiment table, and probably you can do experiments on that particular. And its DOE is vast. DOE
yes, sir.
is vast syllabus. Like you may not get into in particular area, so you may just start in some portion only, and you can explore. Like if you want to know the entire DOE, it's very difficult. It's very difficult, right? I always suggest to take the best options in the present, means take the best option from the existing options and then explore.
Okay, sir. Thank you, sir. Thank you.
Any other? Please, you can unmute and you can ask. Okay, so sir, I have one doubt, sir. When you were doing this ultrasonic and you have hybrid, like you have rightly said, there are so many parameters to control. So, and you have that option of choosing the different models. So, what made you select RSM and what made you choose phase central composite design? Because even his doubt. In fact, we were getting these kind of doubts in the recent past in the previous lectures also. So could you clarify this on when you have this all process ready now? So what motivated in selecting RSM in particular, like face-centered composite, central composite design? Sir, unmute, sir. Your mic is muted.
Sir, Dr. Varun, sir.
Sir.
Sir, you asked the right question, sir. What I have planned to ask
No,
when you said that. Yes, sir. Thank you very much for this question.
thank you, sir.
Actually, while doing experiments, like when I explained about the process, we observed that there are a lot of factors in it, and basically, after doing a lot of literature and pilot experimentation, I found four parameters and three levels, four parameters and three levels. So before that, before doing that main experiment, we also done some Taguchi L9 analysis also. In that also we found which is major parameter, major contribution, which is giving major contribution. And we also conducted simulation also. And I said, in simulation we varied amplitude. We varied amplitude and we found that there is no much effect on that variation of amplitude, and we fixed that amplitude as constant. Like that we started screening, and one fine day, like I finalized the four parameters with three levels, and I want a good design out of it. So like using a software, like we have got that table using that RSM and all, and that is also not final. Choosing is not final. Like after doing lot of lack of fit, right? After doing whether the model is fit or not, etc. Many times we change the design. Many times we
Yes, sir.
change the design, and finally, why we fix this means the experimental and the prediction table were matching to the parameters which I selected, and also the validation is proper. The validation is proper in terms of the f value, r square value, and the p value which I achieved. So the model is acceptable when I use this particular table. So for others, maybe if your parameters are varying, like if you are having three parameters, three levels, then you have some different options, right?
Yes, sir.
So in my particular case, like I choose this model with respect to my the parameters and the ranges. That parameters and ranges are selected by me with a lot of research and pilot experimentations, and as well as doing some simulation as well. Right? So this screening is done. The screening is done, and my guru is Professor Pradeep Kumar. So he is a master in DOE. So he helped me to finalize this RSM, right? So Professor Pradeep is friend of Taguchi also.
Oh,
So so he is a key point. He's a key role. He played a key role in choosing the final design, and that we published in Advanced Manufacturing Technology paper, that RSM result, and also the simple, just by varying the frequency, whichever I have shown in the result now, frequency variation and time increase, that we published in Machine Tools and Manufacture. So always what I suggest is you finalize the factors and levels and choose the best set. And in my case, I have screened a lot of factors and I have chosen the important factors, and I took decision of my guide. It played an important role, to be
yes, sir. Yes,
frank.
sir. Definitely.
It,
Yes, sir.
it played an important role. And after taking the design also there will be a lot of confusions, but the validation is important. Once you
Mm.
validate the results, once you get a prediction model, then only you can assume that you are in a right line like that.
Yes, sir. Thank you, sir. Thank you very much. Uh, so if there is any other question we may ask, or we will end the session.
Yeah, in the case study we'll be
Okay.
discussing in detail about the
Sure, sir, in the
parameter flow.
afternoon session. So thank you once again, sir, because you have given a detailed discussion, and you have shown your own PhD case study, and we have started with abrasive flow machining and hybrid with ultrasonic assisted. So that gave a very good research orientation also, and the emphasis that you have given on the process parameters. And since you have categorized everything, now that we know these many parameters are influencing, now in the afternoon session we were more excited to see how your model is going to suggest which is more influencing, and finally how we are going to optimize it. I think that is going to be more challenging for any of the research scholars. And interesting point is, like, nowadays more metal additive manufacturing are coming up. Abrasive flow machining is the only process that they are trying to use for finishing those metal additive manufacturing process, which is again a point that we can add. So recent past, we are seeing more 3D printing taking over the conventional method, and metal additive manufacturing is going to be near future. So finishing is one area where it lacks, and that is abrasive flow machining is the solution. And your papers are going to be more useful for the research scholars and will be the base. And if any other scholars are also interested, I think if they have not decided, I think this is a very good area to explore, right, sir?
Yes,
So thank you, sir. Thank you very much. Please join us back again at 1:30. I'll be sharing the feedback form soon after this session for this particular morning session. And afternoon, we'll start exactly at 1:30. Uh,
okay,
thank,
okay, Dr. Varun.
thank you, sir. Thank you very much.
Okay, we'll meet at 1:30.
Yes, sir. Dear participants, please kindly join us after 1:30 post lunch. Thank you.